This is the EdExcel A-Level Maths Paper 3, covering the Statistics and Mechanics section, and it's from the June 2018 series. Question number 1. Helen believes that the random variable C, representing cloud cover from the large dataset, can be modelled by a discrete uniform distribution. For part A, we have to write down the probability distribution for C. Well, first of all, we know for part A regarding cloud cover that it's measured in eighths, referred to as octus. So if I draw a diagram of cloud cover, such as the one here, what we have is 0 cloud cover and the cloud completely covered. So the numbers shown here represent the cloud cover, and we see we've got 9 numbers, the 8 here and this extra 0. Now the 0 would represent the sky being completely clear. The 4 would represent the sky half cloudy, and the 8 would represent the cloud being fully cloudy. And so if we were to create a probability distribution, well, here is our table. We've got C representing the cloud cover 0 to 8, and because we've got in total 9 parts to this, the probability that C is equal to C will equal 1/9. And so here we have our distribution table. Next, for part B, using this model, we have to find the probability that the cloud cover is less than 50%. For a cloud cover less than 50%, that's less than this 4 here. And so for part B, the probability that C is less than 4, that's equal to the probability that C equals 0 plus the probability that C equals 1 plus the probability that C equals 2 plus the probability that C is equal to 3. This is all less than 4. We've got 0, 1, 2 and 3. And so what we end up with over here then is 4 multiplied by 1/9, because I've got 1, 2, 3, 4. The probabilities are the same, so we've got 4 times 1/9, which is 4/9. And then Helen used all the data from the large dataset for her in 2015 and found that the proportion of days with cloud cover of less than 50% was 0.315. We have to comment on the suitability of Helen's model in light of this information. So we know already that if all the data was used, then the probability that cloud cover for Helen is less than 50% is 0.315. And this 0.315, if I compare that with the 4/9, now 4/9 as a decimal, that's 0.4 recurring, so the 0.315 is less than the 4/9. And so what we can say from this then is the proportion of days with cover of less than 50% is lower than expected, and so the model may not be suitable. Now for part D, we have to suggest an appropriate refinement to Helen's model. Well, we could use a non-uniform distribution, and that's because cloud cover varies depending on month or location. Question number 2. Tessa owns a small clothes shop in a seaside town. She records the weekly sales figures, W pounds, and the average weekly temperature, T degrees C, for 8 weeks during the summer. The product moment correlation coefficient for these data is minus 0.915. For part A, stating your hypotheses clearly and using a 5% level of significance, we have to test whether or not the correlation between sale figures and average weekly temperature is negative. Well, what we can do is, first of all, state our null and alternate hypothesis. For our null hypothesis, we've got rho equaling 0, we're saying that there's no correlation. And for our alternate hypothesis, we're saying that the product moment correlation coefficient is less than 0. And the reason it's less than 0 is because we've got minus here. So we are testing at the 5% level of significance. And if we go to the tables, for a 5% level of significance, with our sampling size being 8, we have negative 0.6215. And so if I draw a diagram, here I've got my critical value of minus 0.6215, and the value obtained was minus 0.915. So that value is over here. We've got minus 0.915, and because the minus 0.915 is less than the minus 0.6215, we would therefore reject H0. We can conclude there's evidence to reject, rather there's evidence to suggest negative correlation. Then for part B, we have to suggest a possible reason for this correlation. Well, one possible reason is, as temperature increases, people are more likely to do outdoor activities than shop. Now for part C, Tessa suggests that a linear regression model could be used to model these data. We have to state, giving a reason, whether or not the correlation coefficient is consistent with Tessa's suggestion. Well, we know that R is close to 1, rather, negative 1, rather. And so because we've got something which is pretty much a straight line, because R is close to negative 1, we can then say that the correlation coefficient is consistent with her suggestion. Then for part D, we have to state, giving a reason, which variable would be the explanatory variable. Well, T will likely be the explanatory variable. That's because sales are likely to depend on temperature. Then for part E, Tessa calculated the linear regression equation as W equals 10,755 subtract 171T. We have to give an interpretation of the gradient of this regression equation. So we are looking for an interpretation of the gradient, and the gradient here is negative 171. So what can we say from this? Well, every degree rise in temperature leads to a drop in weekly earnings of £171. Question number 3. In an experiment, a group of children each repeatedly throw a dart at a target. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. Peter models h as a binomial distribution with parameters 10 and 0.1. For part A, we have to state 2 assumptions Peter needs to make to use her model. Well, for part A, the probability of a dart hitting its target is constant. That's our first assumption, and the second assumption, the throws of each dart are independent. Then for part B, using the model, we have to find the probability that h is greater or equal to 4. So for part B, the probability that h is greater or equal to 4, that's the same as 1 minus the probability that h is less than or equal to 3. And so if we use our calculator, we've got 1 minus, and then for this particular probability, we can calculate using a binomial CD. We've got x equaling 3, n equaling 10, and p equaling 0.1. So we've got 1 minus 0.987, etc. And so therefore, we end up with 0.0128. And that's given to 3 significant figures. Then for part C, for each child, the random variable f represents the number of throws on which the first dart hits the target. Using Peter's assumptions about this experiment, we have to find the probability that f is equal to 5. So, first of all, the probability that f equals 5, that means the child hits the target on the 5th throw, but misses the first 4 throws. Now to do this, we can draw a tree diagram. So here I've drawn a tree diagram to represent what's going on. We could either hit or not hit, and the probability of hitting we know is 0.1, so the probability of not hitting is 0.9. What we need to calculate is the probability that h is, rather that f is equal to 5. Now we did mention that we hit it on the 5th throw, but we miss the first 4 throws. And so what happens is we miss the first 4 throws, but then we hit the target on the 5th throw. So I've got here 0.9 to the power of 4 and then we multiply this by 0.1. This is when we hit it. So if we calculate what this is, we get 0.0656 as our probability. Next, Thomas assumes that in this experiment no child would need more than 10 throws for the dart to hit the target for the first time. He models the probability that f equals n as the probability that f equals n is equal to 0.01 plus n minus 1 times alpha, where alpha is a constant and we have to find the value of alpha. So for part D, we know so far the probability that f is equal to n, that's equal to 0.01 plus n minus 1 times by alpha. And we know that n, we are going from 1 to 10, and that's because we have no more than 10 throws. So we can create a table for a probability distribution. So here we've got a table from n equals 1 to n equals 10, and let's substitute this into 0.01 plus n minus 1 times alpha. Well, when n is 1, this term disappears, so we just have 0.01. When n is 2, we have 0.01 plus alpha, because we've got 2 minus 1 times alpha. N is 3, we have 0.01 plus 2 alpha, and we can continue on up until n equals 10, where we have 0.01 plus 10 minus 1 times alpha, which is 0.01 plus 9 alpha. Now, we know that the sum of probabilities is equal to 1, so if I add all of this together, 0.01 times by 10, that's just going to be 0.1, and then alpha plus 2 alpha plus all the way up to 9 alpha, that will be 45 alpha. So I've got 0.1 plus plus 45 alpha equals 1. And if I solve for alpha, we can conclude alpha is the same as 0.02. And then for part A, we have to, using Thomas's model, find the probability that f is equal to 5. So, for part A, the probability that f is equal to 5, that is shown here. So that probability is 0.01 plus 4 alpha, and with alpha equaling 0.02, we have 0.01 plus 4 times by 0.02, which is 0.09. Then, for part F, we have to explain how Peters and Thomas's models differ in describing the probability that a dart hits the target in this experiment. Well, if I take a look at Petter, the probability of hitting the target remains constant, and that's with the binomial. Whereas if I look at what's happening with Tom, you can see with each throw, the probability increases with each throw. So that's how they differ. Question number 4. Charlie is studying the time it takes members of his company to travel to the office. He stands by the door to the office from 8:40 to 8:50 one morning and asks workers as they arrive how long their journey was. For part A, we have to state the sampling method Charlie used. Well, quite simply, for part A, that would be opportunity sampling. We're standing at the door and we're asking workers who come in what their opinion is on something. Then for part B, we have to state and briefly describe an alternative method of non-random sampling Charlie could have used to obtain a sample of 40 workers. Well, for part B, we could use quarter sampling. So by that, we could take 4 people every minute in 10 minutes, so that will give us a total of 40. Then for part C, Taruni decided to ask every member of the company the time X minutes it takes them to travel to the office. We have to state the data selection process Taruni used. Well, we're asking every single person. And so what we have then is a census of people. So part C, we have a census, we're asking each person. Now, Taruni's results are summarized by the box plot and summary statistics below. And for part D, we have to write down the interquartile range for these data. Well, if I take a look at this value here, that's 58. And if I take a look at this value here, that's 26. The upper quartile is 58, the lower quartile is 26. So when we come to calculate the interquartile range, that's equal to the upper quartile 58, subtract the lower quartile 26, so it turns out we get 32 minutes and make sure we state the units. Then for part A, we have to calculate the mean and standard deviation for these data. Well, we've got n is 95, the sum of the x's is 4,133, and the sum of the x squareds is 202,294. Now, to calculate the standard deviation, we can use this formula here, the square root of the sum of the x squared over n, subtract the mean squared. So what we need to do before we do anything else is calculate the mean. So for part A, the mean, that's equal to the sum of the x's over n. So we've got 4133 over 95. So if I work out what this is, we get 43.5 minutes. And therefore, for the standard deviation, we have the sum of the x squareds over n, subtract the mean squared. So, if we work this out, we get 202,294 divided by 95. Subtract our mean squared. Now our mean here is 4133 divided by 95. So if I work out what this is, we have the square root of 202,294 over 95, take away the mean squared. So the standard deviation is 15.4 to 3 significant figures. Now for part F, we have to state giving a reason whether you would recommend using the mean and standard deviation or the median and interquartile range to describe these data. Well, what we can see is there are outliers here and here, and those will skew the data, which will affect the mean and standard deviation. So there's outliers in the data, so in other words, the data is skewed, and this will affect the mean and standard deviation. And so I recommend using the median and the interquartile range. Now for part G, Rana and David both work for the company and have both moved house since Taruni collected her data. Rana's journey to work has changed from 75 minutes to 35 minutes, and David's journey to work has changed from 60 minutes to 33 minutes. Taruni drew her box plot again and only changed 2 values. You have to explain which 2 values Taruni must have changed and whether each of these values has increased or decreased. Now, if we take a look at our box plot, currently the lowest value is 20. And this 20 is not going to change. Now, the reason that's the case, if I look at the 75 and the 60, the 75 and the 60 lie between the upper quartile and this maximum value. So when they decrease to 60, they decrease to 35 and 33 respectively, and those are in between the lower quartile and the median. But this lowest value is not changing, as I've just said. So that's our first point. The lowest value of 20 did not change. Also, if we consider where these data are and where they are going to, these outliers as well are not changing. So the outliers do not change. Now, as I've just said, this 75 and this 60 are in between the upper quartile and the highest value. And when we change the values because of them moving houses, the 35 and the 33 are now between the lower quartile and the median. They are now somewhere here, in between the lower quartile and the median. And because of that, we are shifting our values, and so the median and the upper quartile will be lower because of where the new values lie between now. Our previous values have now moved, so our median and upper quartile will shift to the left, and so will be lower. Question number 5. The lifetime L hours of a battery has a normal distribution with mean 18 hours and standard deviation 4 hours. Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. For part A, we have to find the probability that a randomly selected battery will last for longer than 16 hours. So for part A, we've got the lifetime L, which follows a normal distribution with parameters 18 and 4 squared. We've got over here the standard deviation being 4 hours and the mean being 18. Now what we need to calculate is the probability that L is greater than 16. Now for this we can quickly draw a diagram, and if I quickly draw a diagram like this, we've got 18 over here, and here we've got the 16, and so we need to calculate this region here. So if we go to our calculator and go to the distribution section, we have a normal CD. Our lower limit is 16, upper limit can be something really big such as a million, sigma is 4, mu is 18, and it turns out we get 0.6914, etc. as our required probability. And then for part B, at the start of her exams, Alice puts 4 new batteries in her calculator. She has used her calculator for 16 hours, but has another 4 hours of exams to sit. We have to find the probability that the calculator will not stop working for Alice's remaining exams. So in this question, she has used her calculator for 16 hours, but she's got another 4 hours of exams to sit. And so her calculator needs to last for more than 20 hours. And because of that, we are calculating for each battery the probability of using the calculator for more than 20 hours, given she's used it for 16 hours. So what we'll do to begin with is find out the probability that L is more than 20. And again, let's draw a diagram like so. We've got 18 over here, 20 over here. We're calculating the probability that she's used it for more than 20 hours. So our lower limit this time is 20, and so the required probability is 0.308, etc. Let's store this into A just in case we need it later on. And so what we are doing in this question is finding out the probability that L is greater than 20 given L is greater than 16. So the probability that L is greater than 16, that's 0.691, etc. So I need to do the 0.308, etc. divided by this. And if we work out what this is, if I store this into B, I need to do A divided by B. So it turns out we get 0.446, etc. And that's for each battery. And so therefore, for the calculator to work, we will have to do 0.446, etc. to the power of 4 because we've got 4 batteries. And if I work out what this is, I need to raise this to the power of 4. I get 0.0396, etc. So that's how we approach part B. And then for part C, Alice only has 2 new batteries, so after the first 16 hours of her exam, although her calculator is still working, she randomly selects 2 of the batteries from her calculator and replaces these with 2 new batteries. We have to show that the probability that her calculator will not stop working for the remainder of her exams is 0.199 to 3 significant figures. So here, she still has 4 hours of exams still to sit, and so the calculator needs to last for more than 4 hours. So therefore, the probability that L is greater than 4, we can quite easily calculate what this is. We have a normal CD, lower limit is 4, upper limit is something really big, sigma is 4, here we have 18 from U. So the probability that it lasts for more than 4 hours, that probability is 0.999, etc. Store this into C just in case we need it later on. And what does this represent? This represents the probability that it lasts for more than 4 hours. And this is for 1 new battery. And therefore, for 2 new batteries, we would have 0.99, etc. squared. So then I need to take my value of C and then square it. And I get 0.9995. So here I get 0.9995, etc. And for the 2 batteries that remain, well, for each battery, given that it should last for more than 20 hours, given it lasts for more than 16 hours, for the 2 remaining batteries, we have 0.446, etc. squared. So the way we work that out, well, let's store this into D. The way we worked out that 0.446 was doing A divided by B. And then if I square this, I get a value of 0.199, etc. Let's store this into E. And so for the calculator to not stop working, we've got 0.9995, etc. times by 1.99, etc. So if I work this out, I've got d times e, and I get 0.199 to 3 significant figures. Now for part D, after her exams, Alice believed that the lifetime of the batteries was more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2 hours. Stating your hypothesis clearly and using a 5% level of significance, you have to test Alice's belief. Well, here we can see that the mean has increased when she took her sample, and because we have a sample over here, we need to consider the sample mean. And so for part D, we've got our null hypothesis, mu equaling 18, and our alternate hypothesis, mu being greater than 18. Now we've got the mean lifetime, L bar, normal distribution, we have 18, and our variance will be 4 divided by root 20 squared, and that's because we've got a sample mean. Now we know for a sample mean, to calculate z, that's equal to, well, in this case it will be L bar subtract mu divided by sigma over square root n. So if I calculate what z is equal to 19.2 subtract 18 divided by 4 over square root 20, and if I work out what this is, we get a value of 1.341, etc. So how does this help us? Well, let's draw a diagram like so. We've got 0 over here. We've calculated a z value, and what we'll do is we'll take a look at what the critical z value is. The critical z value we can find from the tables. So if we scroll down, for a 5% significance level, we have z equaling 1.6449. So here we've got 1.6449. We'll just write it in black. So we've got 1.6449. And the value we've just found is less than this. So here we've got z equals 1.341. And so we're in the region where we do not reject h0. And because we do not reject h0, there is not enough evidence to suggest that the mean is greater than 18. Question number 6. At time t seconds where t is greater or equal to 0, a particle p moves in the xy plane in such a way that its velocity v meters per second is given by v equals t to the minus 1/2 I minus 4tj. When t equals 1, p is at the point A, and when t equals 4, p is at the point B. We have to find the exact distance AB. Well, we know what v is, and we can integrate this to find out what the displacement x is. That's equal to the integral of the velocity with respect to time. So I need to integrate with respect to time t to the minus 1/2 I minus 4t j. And if we work this out, we have 2t to the power of 1/2 I minus 2t squared j plus some constant of integration, we'll call it c. Now, we know that when t is equal to 1, the displacement at A, that's 2 times by 1 to the 1/2 I plus, rather, minus 2 times by 1 squared j plus c, which is the same as 2i minus 2j plus some constant c. And when t equals 4, similar idea, the displacement at B, we've got 2 times 4 to the 1/2 I minus 2 times by 4 to the power of 2 j plus some constant c. So it turns out here we have 4i minus 32j plus c. And so therefore, the displacement from B to A, that's xb subtract xa. So if I work this out, I have my displacement for B subtract my displacement for A, and that's what we see here. Now the c's cancel out, and it turns out I'm left with 2i minus 30j. So what we need to do is find out the distance. So the distance is equal to 2 squared plus negative 30 squared square rooted. And it turns out the exact distance is 2 times by the square root of 266. Question number 7. A wooden crate of mass 20 kilograms is pulled in a straight line along a rough horizontal floor using a handle attached to the crate. The handle is inclined at an angle alpha to the floor, as we see in figure 1, where tan alpha is 3/4, and if that's the case, we can form a 3, 4, 5 right angle triangle. Sin alpha is 3/5, cos alpha is 4/5, and tan alpha is 3/4. The tension in the handle is 40 newtons, and the coefficient of friction between the crate and the floor is 0.14. The crate is modelled as a particle, and the handle is modelled as a light rod. Using the model for part A, we've defined the acceleration of the crate. Well, what we need to do in this question is use the sum of the forces equals mass times acceleration. So if we go back to our diagram, we've got the upwards and downwards force. So here we've got an upwards force of R, that's a reaction force. We've got the downwards force, 20g, and then we've got the frictional force. If I'm moving it towards the right, that means friction is opposing it this way. I've got F equals mu R. So I've got to use F equals ma both vertically and horizontally. So if I use F equals ma vertically, going upwards, we've got this component component of the 40 newtons upwards, so that's 40 sine alpha, plus this r. So I've got r plus 40 sine alpha, and that's equal to what's going down, 20g. Now we know what sine alpha is, that's 3/4. So I've got r plus 40 times by 3/4, rather that's 3/5. That's equal to 20g. And so r is equal to 20g, subtract 40 times 3/5, which is 24. Then we've got newtons. And thinking about what we have horizontally, well, we've got the horizontal component forward of the 40, so that's 40 cos alpha, subtract f, and that's equal to 28. The mass is 20. We're finding out acceleration. So I've got 40 cos alpha minus f equals 20a. So I've got 40 times by 4/5, subtract f. Now here f is equal to mu r, and that's equal to 20a. Now, do I know what mu is? Well, I know that mu is 0.14, that's the coefficient of friction. So I've got 40 times by 4/5, subtract 0.14 times by r, and I already know what r is, that's 20g minus 24. And that's equal to 20a. So if we work out what this is, I've got 40 times by 4/5 minus 0.14 multiplied by 20 times 9.8 minus 24. So it turns out we get 7.92 equals 20a. So if I divide this by 20, we can conclude a is equal to 0.396. And that's the acceleration. Then for part B, the crate is now pushed along the same floor using the handle. The handle is again inclined at the same angle alpha to the floor, and the thrust in the handle is 40 newtons as we see in this diagram. We have to explain briefly why the acceleration of the crate would now be less than the acceleration of the crate that we found in part A. Well, if we go back to the diagram, we'd have the same situation, but this time acting down with the gravity, we'd have this 40 newtons. So let's add this on in a different colour. We essentially have a 40 newtons going down with it. So again, what we'll do is we'll consider the sum of the forces both vertically and horizontally. So if I consider the sum of the forces vertically, then I have R equals 20g plus 40 sine alpha. So we have R equals 20g plus 40 times sine alpha, which is 4/5. And it turns out R is equal to 228. And if I consider what's going on horizontally, we have 40 cos alpha subtract f equals 20a. Same idea. We have 40 times by 4/5 minus 0.14 times r equals 20a. So I have 32 minus 0.14 times 228 equals 20a. So if I work this out, I've got 32 minus 0.14 times 228, which is 0.08. So I've got 0.08 equals 20a. And in this case, a is equal to 0.004 meters per second squared. So clearly the acceleration has decreased. And why is that? Well, that's because if r increases, the frictional force would also increase. So the resultant force would decrease, but the acceleration then would decrease. So let's write all that down. So if r increases, the frictional force F equals mu r would increase. So the resultant force decreases, and so therefore the acceleration would decrease. And that's all the steps we have shown. So over 20 times 9.8, subtract 24. So that's the reason. Question number 8. In this question, I and j are horizontal unit vectors due east and due north respectively, and position vectors are given relative to the fixed point O. Now what particle P moves with constant acceleration, so that's the first thing which is important in this question. We are moving with constant acceleration, and at time equals 0, the particle is at O and is moving with velocity 2I minus 3j meters per second, and at time t equals 2 seconds, P is at the point A with position vector 7I minus 10j meters. We have to show that the magnitude of the acceleration of P is 2.5 meters per second squared. So, because we've got constant acceleration, we need to use the Suva equations, and the Suva equation I will be using for part A is we'll stick with R equals ut plus 1/2 a t squared. So I've got the position at time t equals 0, at the time t equals 2. So when t equals 2, I've got the position 7I minus 10j, and that's equal to u, the initial, which is 2I minus 3j, and I multiply this by 2, and then I add on to this 1/2 times acceleration, and the acceleration here is what we are finding as a vector, times by t squared, so I'll multiply by 2 squared. So I've got 7I minus 10j equals 4I minus 6j plus 2a. So we have 3I minus 4j equals 2a. So therefore a is equal to 1.5I minus 2j meters per second squared. What we need to do is find the magnitude of the acceleration. So the magnitude of the acceleration, we have 1.5 squared plus negative 2 squared, and then square rooted. And if I work out what this is, we get 2.5 meters per second squared for the acceleration. And then for part B, at the instant when P leaves the point A, the acceleration of P changes so that P now moves with constant acceleration 4I plus 8.8j meters per second, and at the instant when P reaches the point B, the direction of motion of P is northeast. We have to find the time it takes for P to travel from A to B. Now here what we need to do is use V equals U plus AT. And what that will do is it will allow us to find out the final velocity as it moves from A to B. So if we use V equals U plus AT, we know that when t equals 2, V equals, well, I've got the 2I minus the 3j, and then I'm going to add on to this 1.5 minus 2j multiplied by 2. So what I'm doing over here is finding out the acceleration when t equals 2. And if I work out what this is, I've got 2 plus 3 in the I direction, and then I've got negative 3, negative 4, so that's negative 7j meters per second. So what would this represent? Well, it would represent the initial velocity when P leaves A. Now we know when leaving A, P has a new acceleration of 4I plus 8.8j. So if we use V equals U plus AT again, but this time our U will be 5I minus 7j. We have 5I minus 7j plus 4I plus 8.8j multiplied by t, and we need to find out what t is. So in terms of the i's, we have 5 plus 4t of them, and in terms of the j's, I've got 8.8t subtract 7 of them, and we have meters per second. And what we also know is it's travelling northeast, and for northeast the I component is equal to the j component. So if I use that, I have 5 plus 4t, that's the I component, and that's equal to 8.8t subtract 7, which is the j component. So I've got 4.8 t equals 12, and so therefore t equals 2.5 seconds. And that's exactly what we wanted to find out. Question number 9. A plank AB of mass m and length 2a rests with its end A against a rough vertical wall. The plank is held in a horizontal position by a rope. One end of the rope is attached to the plank at B, and the other end is attached to the wall at the point C, which is vertically above A. A small block of mass 3m is placed on the plank at the point P, where AP is equal to x. The plank is in equilibrium in a vertical plane, which is perpendicular to the wall. The angle between the rope and the plank is alpha, where tan alpha is 3/4, as we see in figure 3. The plank is modelled as a uniform rod, the block is modelled as a particle, and the rope is modelled as a light inextensible string. For part A, using the model, we have to show that the tension in the rope is 5 mg multiplied by 3x plus a divided by 6a. Before we do anything else, I think it will be a good idea to draw some of the forces on the diagram. So we've got this block with mass 3m. So the weight of it going downwards over here will be 3 mg. And what we also have is the plank with mass m. So over here at the center of the plank, we've got a weight of m. And we've got the tension in the rope, so we can show that like so. We've got the tension here. We are also told that tan alpha is equal to 3/4. So with our 3, 4, 5 triangle, we've got sine alpha equaling 3/5 and cos alpha equaling 4/5. So the way we can approach this question is to take moments about A. Before we do that, we know as well regarding the wall, it's a rough wall. So that means we've got a frictional force over here, and we've got some sort of a reaction as well. We'll call this R. So if we take moments about A, that will eliminate all the forces about point A. So for part A, if we take moments about the point A, then from A to the center, this distance will be half of the 2A, which is A, and I multiply that by m, and then here I've got g with it, because it's the weight of the ladder. So I've got a distance of A multiplied by mg. So I've got A multiplied by mg, and then I have x multiplied by 3mg, and that's equal to, well, here I've got the force here, T, and I've got the distance 2A. So what I need is the distance times by the perpendicular force. So this is equal to 2A, which is the distance, multiplied by T sine alpha. So the A's cancel. So I have mg plus 3xg, that's equal to 2at times by sine alpha, and I know that sine alpha is 3/5. So I've got the mg, rather here I've got 3m. I've got mg plus 3mxg, so I can factorize out an mg. And inside, rather, we need to include the a's. So just start again. So here, if I include the a's, I've got a mg plus 3mgx equals 2at times by 3/5. And if I factorize out an mg from the left hand side, then I have a plus 3x, and that's equal to 6 over 5 at. And if I solve for t, that means t is equal to, if I multiply through by 5 as well, I have 5 mg multiplied by 3x plus a. Then I divide this by 6a. So that's how we find out what t is. Then the magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2 mg. And we have to find x in terms of A. So what we are saying over here is this force is equal to 2 times by m times by g. That's what that is saying. So with what we can do now to find out what x is resolve horizontally. I've got the horizontal component of t, which is t cos alpha, and that will equal f. So for part B of the question, if I resolve horizontally, I've got f equals t cos alpha. So I've got 2 mg equals t times by 4/5. And so therefore, t is equal to 5 mg over 2. And I also know what t is. That's the result we see here. So I've got this, which is t, and I'm going to set that equal to this over here. And what I need to do is find out what x is. Well, the mg's cancel, and so did the 5 mg's. So I've got 3x plus a over 6a, and that's equal to 1/2. So I've got 3x plus a equals 3a. 3x is equal to 2a, and so therefore x is equal to 2a over 3. And then for part C, the force exerted on the plank at A by the wall acts in a direction and makes an angle beta with the horizontal, and we have to find the value of tan beta. So the way we will approach this is, well, if I go back to the diagram over here, and if I join these 2 points up, the angle this question is after is this angle over here. We'll call it beta. So if I go back to the question, I've got the force exerted on the plank at A on the plank at A by the wall, and it makes an angle beta with the horizontal. So this is the force exerted on the plank by the wall, That's what R is. And this R makes an angle beta with the horizontal. So what we can do now then is use trigonometry to find out what that is. Now, before we do anything else, we actually need to find out what the tension is. Well, we know that the tension is equal to 5 mg over 2. So if we resolve vertically, we can find out what R is. We've got the R over here plus T sine alpha, and that's equal to mg plus 3 mg. So if we resolve vertically, then I've got R plus T sine alpha, that's equal to mg plus 3 mg. So I've got R plus T, which is 5 mg over 2. That's equal to 4 mg. Rather, I've got 5 mg, and I'm going to multiply this by 3/5 because it's T sine alpha. And then this is equal to 4 mg. So if I find out what R is, I've got R plus, now here I have 3 mg over 2 because the 5 cancels with this 5. So I've got 3 mg over 2. That's equal to 4 mg. So I can find out what R is at this point. R is equal to 5 mg over 2. So if I go back to my diagram, we can find out what R is. That's 5 mg over 2. So let's create a new diagram to help us find out what tan beta is. So I've got a triangle over here, I've got beta over here, and I've got F, and I've got R. So therefore, tan beta is equal to R divided by F. So I've got R, which is 5 mg over 2, and then I'm going to divide this by F, which is 2 mg, and it turns out tan beta is 5 over 4. And then for part D, the rope will break we are told the rope will break if the tension in it exceeds 5 mg. We have to explain how this will restrict the possible positions of P. You must justify your answer carefully. So for part D of the question, we know that the tension in the rope is 5 mg times 3x plus a over 6a, and we know that the position of P, x, is relative to the point A. What we are also told in the question, if we go back to part D, we are told that the rope will break if the tension exceeds 5 mg. So we know the rope will break if T is greater than 5 mg. So I already know what the tension is. that's this over here, and the rope will break if this is greater than 5 mg. Now the 5 mg's cancel, so I'm left with 3x plus a divided by 6a being greater than 1. 3x plus a is greater than 6a. 3x is greater than 5a. So the rope will break if x is greater than 5a over 3. So let's write that down. The rope will break if x is greater than 5a over 3. So the rope will break if x is greater than 5 over 3a, and so p cannot be placed more than 5 over 3a meters from a, otherwise the rope will break. Question number 10. A boy throws a ball at a target. At the instant when the ball leaves the boy's hand at the point A, the ball is 2 meters above horizontal ground and is moving with speed u at an angle alpha above the horizontal. In the subsequent motion, the highest point reached by the ball is 3 meters above the ground. The target is modelled as being point T, as we see in figure 4. The ball is modelled as a particle moving freely under gravity, and using the model we have to show that u squared equals 2g over sine squared alpha. Well, here we are considering what u is, so let's work with Suva equations. Now we know at the highest point over here, that's where v equals 0. So what we can do in this question is use v squared equals u squared plus 2as, and we can resolve vertically. So if we resolve vertically using v squared equals u squared plus 2as, I've got 0 squared, that's equal to capital U squared, capital U, and the vertical component of this will be sine alpha. So we've got U sine alpha squared plus 2 times negative g, so that's negative g, times by the displacement. Well, the displacement here from 2 meters to 3 meters, we've got a displacement of positive 1. So we've got u squared sine squared alpha equals 2g, from which we can conclude u squared equals 2g over sine squared alpha. Then for part B, the point T is at a horizontal distance 20 meters from A, and it's at a height of 0.75 meters above the ground. The ball reaches T without hitting the ground. We have to find the size of the angle alpha. Well, what we can do here is, on our diagram, see that, well, what we'll do actually, we'll draw a line from here and then here. What we know is this distance from here to here is 0.75 meters, and so this distance from here to here, then that's equal to 1.25 meters. These add up to give 2 meters. So now let's consider using s equals ut plus a half at squared horizontally. If we consider the horizontal motion with s equals ut plus 1/2 at squared, well, a is equal to 0 in this case. So we've got the horizontal displacement, which is 20 meters. So in other words, from here to the point T, which is here, this is a total of 20 meters. So the horizontal distance is 20, and this is equal to u cos alpha multiplied by t. Remember, a cancels out. And if we consider the vertical motion, then again using s equals ut plus 1/2 at squared, I've got s, which is, well, here the displacement, if I start off from a and I go to t, the displacement is negative 1.25. And this is equal to, well, the vertical velocity will be u sine alpha, and then multiply this by t. And then I subtract 1/2 times by g times by t squared. Now, do we know what t is so far? Well, we could find out what t is from here. If I rearrange for t is equal to 20 over u cos alpha. So, with that, if I now consider the vertical motion, I've got minus 1.25 equals u sine alpha multiplied by t which is 20 over u cos alpha, subtract 1/2 g multiplied by t squared, so I subtract 1/2 g times by 20 over u cos alpha squared. So I've got minus 1.25 equals, well, here the u's cancel, and I'm left with 20 multiplied by, well, here I've got sine alpha over cos alpha, which is tan alpha. And then here I've got 1/2 times by g times by 20 squared, so 20 squared times 0.5 times by 9.8. That is, well, before we do anything else, let's expand fully. I've got 1/2 times by g multiplied by, well, here I'd have 20 squared, and on the bottom I would have u squared cos squared alpha. But I know what u squared is. That's 2g over sine squared. So I can replace as necessary. So I've got this equation, but instead of me having a u squared, I've got 2g over sine squared, and I'm going to multiply this by cos squared alpha. So at this point, the g's would cancel, and I'm left with a half times by another half on the bottom. Well, I've got a half times by 20 squared, and then I've got cos squared over sine squared, which is cot squared. So I've got my equation, minus 1.25 equals 20 tan alpha, subtract 100 over cos squared over sine squared, which is cot squared. So cot squared is 1 over tan squared, so I've got 100 over 1 over tan squared, which is just 100 tan squared. So I've got minus 1.25 equals 20 tan alpha, subtract 100 tan squared. So rearranging, I've got 100 tan squared, subtract 20 tan alpha, minus 1.25 equals 0. I can find out what tan alpha is. So if I do the inverse tan, well, let's solve the quadratic. I've got 100 minus 20 minus 1.25. So I get tan alpha equals 1/4 and minus 1 over 20. So if I find out what alpha is, well, if I do the inverse tan of 1/4, I get 14.03. And if I do the inverse tan of minus 1 over 20, I get minus 2.86, etc. Now because alpha is in between 0 and 90, we can therefore conclude alpha is equal to 14.0 degrees, given to 3 significant figures. Then for part C, we have to state one limitation of the model that could affect your answer to part B. Well, here, in reality, there will be air resistance and therefore alpha could change, so that's a limitation. Now for part D, we have to find the time taken for the ball to travel from A to T. Well, what we'll do is we'll use this equation, we'll call it 1, and we'd also use this equation to help us find out what t is, because this t tells us the time taken to travel from A to T. So if I substitute, well, for part D of the question, from equation 1, u, that's equal to 2g over sine squared alpha square rooted, which is equal to 2g square rooted over sine alpha. And I know what alpha is. That's the inverse tangent of a quarter. We'll store this into the calculator. So I have 2g square rooted over sine of 14.0, etc. And if I call this 3, I can substitute in 3 into 2. So if I substitute in 3 into 2, I've got t equals, if I go back, I've got 20 over u cos alpha. So I've got 20 over u cos alpha. So I've got 20 over u, which is this, multiplied by cos of 14.0, etc. So if I find out what t is, I have 20 over the square root of 2 times 9.8 divided by the sine of this times by the cos of this. So it turns out the time is 1.13 seconds given to 3 significant figures.